the daytime.
Yeah, I'll convey that. Okay.
Okay, thank you.
Yeah.
So I'm leaving the session, going to the DLGenAI project because the first session is there.
Yeah, and can you just convey to them that there is a theory session going on at the same time? So if some
Yeah,
rescheduling can be done, that would be really great
yeah,
if you can tell them.
yeah. I will go there and I will
Yeah,
tell. Okay,
that's great. Thank you.
thank you, thank you.
Thank you.
Hello, sir. Will
Yeah,
this be recorded and live streamed too?
yeah. Right now, live streaming is not working for some reason, so I've recorded it and I'll just upload it to YouTube after the meeting ends.
Okay, sir. Thank you, sir.
Okay, yeah. Actually, live streams every time. There's some glitch that was happening with live streaming in some courses, so I'll upload it once the recording is saved in my file. Okay.
Sir, can you share the YouTube link for
It's
the?
not working right now, so I'm recording it and I will upload it after the session. So then you'll get the link.
Okay.
Sir, was there a session yesterday? I didn't have
TA
anything
session
in my
might be there,
calendar.
no instructor session. Instructor session is Friday and Saturday, so that will be our same day.
Yes, sir. You said TA session, right? I didn't have anything in my calendar.
I'm not sure about TA session. I think there was did any one of you attend any TA session yesterday? I think there was one which got conducted yesterday.
Yes,
or
sir.
Thursday, I guess.
Sir, can I get that recording at least? Because I didn't get.
Yeah,
It's
sure,
not recorded.
Sure. It's not recorded.
Yes.
So there's no link for that meeting either on the calendar.
Actually, it's not recorded nor live streamed. Actually.
Yeah, actually, live streaming in many courses there is some issue with that. So recording it should have happened. I don't know. There might have been some issue with that as well. The meeting link also got changed recently, so I think it will get fixed from next session onwards. There was some backend issue from Google Meet that was happening actually. It'll get fixed. Don't worry, and I'll give you the link of those earlier sessions as well. I'll just talk to the team and we'll share it with you after the session.
Okay.
Yeah, so scheduling and live session link and all these problems, they will get sorted in 1 or 2 days. So that won't be an issue. Okay, there was some backend problem. That is why it was happening this time.
A session duration also in 1 hour, sir?
Not exactly. Like it should be more than 1 hour, like 1.5 hours at least, because DLGenAI content is long, right? So it will take some time to cover.
That's why I'm asking.
Yeah. So in Gmate, it shows by default 1 hour, right? That's why it's showing 8 to 9.
Okay, let's start.
Yeah, any other question? Okay, I'm starting to share the screen, so just tell me once it's visible.
Sir, I also took project with this theory. How should I, till how many weeks should I?
That actually depends on the problem statement. If it's an LLM problem statement, you'll have last few weeks which are relevant. If it's a vision problem statement, then I think earliest first 5 weeks and 11th, those weeks will be relevant. So what, have you seen the statement so far?
It's a audio related thing, sir. We need to detect
Song classification.
category.
Okay, from the audio.
We'll have.
Okay, that will actually, audio processing directly is not a part of the theory, but you will be able to learn techniques to handle that while you do the practical part of the course, the collabs and all you'll understand. So actually you'll need at least first 6 weeks for that, because basic model building, extraction of data, those things we will be teaching you in the first 5 to 6 weeks. So that should be clear. Beyond that is the LLM part. So since it's an audio thing, then the LLM part might not help in the project that much this time. But the first 6 weeks are the core DL techniques and handling of models and all. That should be helpful in that case.
Sir, it is related to song classification.
Yeah, that would be like, song classification is not a topic of the course. It is an application, obviously, because project is an application only, but you will learn techniques to handle such data in the course. So in the first 6-7 weeks, we'll be covering those type of things. And beyond that as well, we'll be learning new techniques, but at least you should be comfortable with first 6-7 weeks. That should be a good start at least with the project.
And sir, one more thing, that like MLP, I have took the theory plus practical both in this term.
In MLP or in GenAI? Which one you're talking about?
Both, because this is my last term of diploma and I have to.
Then the suggestion for you will be that you do the theory part earlier, like at least from the YouTube, start watching the theory videos of the other weeks as well, so that you can at least stay at pace with the project.
Okay, sir.
Yeah. And in live sessions, you can even watch the older live sessions of last term and before that. That will also help you to get some idea of the theory.
So the course started last term only.
Yeah, last term was the first one. This is the second run of the course. Yeah, September 25 was the first one.
Hello, sir. Can you hear me?
Yeah, yes, you're audible.
So I just want to get a rough idea on because this is gonna be my last semester, and
Okay.
I took this course in the. I had a couple of breaks in the last 2 weeks, so I have taken this course and this is my last subject. So, roughly, can you give me an idea of how the subject will be throughout 12 weeks and what has been really focused on when it comes to deep learning and
So yeah, so actually your audio was not very clear, but what I could make out is you want to ask the overview of the subject, right? What the subject is going to
yes,
cover.
yes,
Okay.
yes.
So this subject is going to be teaching you about deep learning from scratch, and it will build up from the very basics of the simplest neural network models in deep learning, and it will go on to very advanced models like transformers and adversarial networks. So through the weeks, you will learn how these models are built, like the mathematics behind them, the architecture behind them, the applications of different models. You'll also learn some popular models like GPT, BERT. These are some LLMs you might have heard about. Then neural networks will be building for language, will be building for vision, that is images, will be building for videos. So all these types of data that you see. Could you mute there's some background noise that is coming? Could you just mute? Yeah. Okay. So these are the things that we'll be covering, and we'll be learning the theory as well as every week we'll be implementing them using PyTorch library as well. So it is going to be a fairly rigorous course, and you have to devote a good amount of time to do well in this course. That is what I can say.
so I mean we can also on site we can also keep doing whatever you're doing in the course, right? There won't be any problem in practicing that.
Yeah, you can go and practice on site. You, in fact, all the collabs are already available with you in the supplementary content, so you can go through those
Okay,
and practice them on site.
okay. Thank you,
Yeah.
thank you.
What I can say is, for the exam perspective as well as from the learning perspective, your exams are going to be like you'll have NPPs for coding and you'll have the quizzes as well. But quizzes will also have a coding component. Like you won't have to write code, but you'll have to see code snippets and analyze them. So please give a lot of effort to the coding part. It is not a bonus part. It is a core part of the course. Okay, so sometimes in some courses the theory is main and the coding is bonus parts like MLT. Here, coding is very important. It's a core part of the course and it has a lot of weightage in the exams as well. So make sure that you are coding well. It's a fairly practical course as well alongside the theory.
So we should be like looking at the code, should be getting the what the output is what the
Both, like for the quizzes, that will be helpful.
yeah,
For the
yeah,
NPPs, you have to write the code. So both the things will be
got it.
used.
Yeah, got it. Thanks.
Yeah. Okay. And for the live sessions, we'll have 2 live sessions of the instructors. One will be on Friday with me. That will be the theory session where we learn the theory part of the week. And the second one will be with another instructor on Saturday. That will be for the coding part. Okay. So both the things will be covered in live sessions. One for theory, one for coding. That is going to be the format for every week. Okay. So I think that will give some clarity. So if you are all clear with the general things, we can, it will be streamed on YouTube. So don't worry. We'll give you the YouTube as well as on the calendar. The recording will be there. That you can see.
No, I just heard that there were some session yesterday or on Wednesday or something.
Yeah,
What
that
are
that was just a TA session. So that I think recording was not working in that, but don't worry about that. We will see all the others. So your content
okay,
is
no?
fixed.
So that is also gonna happen on every Friday. Sorry, Wednesday and Thursday, stuff like
Yeah.
that.
That is going to happen. Yeah. There is some problem with the calendar. I will be fixing it. Okay, we'll fix it.
Okay, sure. Thank you.
Yeah. So this will be fixed. Okay, Anupam, everything will be fixed.
So
Yeah.
basically in 24 videos and 24 lectures will cover the whole course.
Could you repeat? I just missed out the first part.
So basically in 24 videos, like weekly twice, will cover the whole content which you just mentioned. It
24
seems
videos. There are I think 110 some videos, right?
no,
For the lecture.
24 lectures. Sorry, these live sessions, these instructor live sessions will be weekly twice, right?
Yeah. 24 live sessions. Yeah. Right. Yes. 24 live sessions.
Seems a bit too much, but yeah, I'm up for it.
No, actually, it's
Hello, sir.
quite less if you see. Like in some of the diploma courses, you have 3 sessions per week, right? That is 36. So 24 is fairly Good. Actually, to be honest, the content is very vast. You have around 110 lectures, right? So
Yeah,
to cover
that's
them
what
24
I
live
meant,
sessions
sir.
would be,
Yeah.
yeah. But we like it'll be like giving you a good coverage. You have to definitely like for every course, the primary source is the lecture. Then in live sessions, obviously, we'll try to cover as much as possible, but you have to watch the lecture as well to
Mhm.
get the finer details of the things. For the coding part, at least go through the collabs. The lecture collabs are very well made, so at least go through them once or twice. That will help you to understand how they are working. Okay, that is
Sure.
the thing. Yeah, Manan, any question from your side?
Sir, the link to the project, this session was given in the mail, but it is wrong. I just got the link. So is there any calendar for the DLGenAI project to follow?
Yeah, it will be created. Right now, I think today there is some scheduling mistake. Like project session should not happen this time because this is the theory time. So there must be some mistake today. So they'll fix it and do it properly from next
So
week.
in the mail,
Hello,
I
sir.
got a
Hello.
wrong link, sir.
I'm
No,
not
no,
sure
no.
about that
Wrong.
because
Not
the
wrong. Not, sir. Not wrong. The project
Hello.
orientation session is going on parallelly.
So is this a theory session or project
this
orientation?
is theory. This is theory session. This is not project session. This is
Hello, sir.
theory.
I have a
Oh,
small doubt,
okay.
sir, actually.
Yeah.
Sir, regarding project, can you clarify that?
I am not a part of the project team. So I don't think I'll be able to because the project team
Okay,
is
sir.
different. The theory team is different.
Oh.
Yeah.
Sir, I just take both theory and project together.
Okay.
So, yes. So, someone said that it is very difficult to complete
Yeah, it
two
will be
theory and
because the
project.
project depends on the theory, right? And the theory for this course is not very easy.
Yes.
So it will be a difficult thing, but again, not impossible. People have done that last term also.
No,
So it's
no,
not
sir.
impossible.
So, yes, sir. So, for that, we have to complete MLP, but I have taken the MLP also this term. So,
So
sir,
then
I
there is
want to
some
say,
mistake, I think.
the,
You should ask this
uh,
in the project team because this is the thing they'll be able to answer better. I'm not sure, but I think MLP has to be done first. Yeah, you can drop the project also. That's a suggestion. But if you
sir,
want to complete it,
for
you can ask
yes,
the
sir.
team.
After dropping the project, sir, can I have to pay next term, or that will be
I think you get refund, no? You don't have to pay next term probably.
okay?
You get a
Okay.
refund.
So, sir, I don't have to register
Yeah.
with the KL company, sir.
If you want to drop, then no registration. If you want to do it, then you have
Okay.
to register.
Thank you,
Okay.
sir.
Yeah,
Thank
but
you, sir.
still, I'll tell you just mail it to the project team once. You'll get a better idea from that.
Yes, sir. I waited for, but they have arranged the session like we cannot speak, we cannot message. That's it.
So can we move forward with the session because these are like general doubts. This
Yeah,
can
I
be
think that we'll
quick.
move on with the session. So for any project doubt, either you can just join the project session and ask it. Otherwise, you can stay here and you can just send them a mail. They'll respond to the mail. Okay. Okay. So yeah. Actually, this was the first session, right? So these general doubts happen. That's okay. But we'll take more doubts in the end of the session. Let's complete the content. Like week 1 is not very difficult as well. So we'll quickly complete the content. Then we'll take up the general doubts. Right. So can we go ahead? Everyone's ready. So yeah. Okay. We can start then. Okay, so to start with week 1, so week 1 is talking about the basics of deep learning, right? What deep learning does and what type of models does the deep learning build. So before moving on to that, let us try to understand that whenever the domain of AI had come up few years back, so initially, not many years back actually, but it got popular few years back. So to start with AI, we first encountered the world of ML, right? I'm not going into ML because you all have done MLT, so you know what ML is and how ML works. But the thing is that you know that ML basically helps you to deal with data, right? A lot of data is given to you, and ML makes a model which makes sense of data. For example, suppose you have height data and you have weight data. Like height is 5'6", right? And weight is 70 kilos. Height is 5'1", weight is 65 kilos. These type of data you have in many cases, right? So what does ML do? ML tries to identify the relation between height, weight, and say, for example, age. Age is my label which I want to predict. And what ML will simply do is it will build a model like this. And this model will simply say like A times this height plus B times this weight is equal to your age, right? That type of a relation it does. And these A's and B's are what it wants to find out. Can somebody tell me what is this A and B called? What is the ML term for this A and B?
So weights and biases.
Yeah, right. Weights, right? Weights, and you also have constants like biases, right? So weights plus bias. This is what we have here. And the goal of any ML model is to find out the best possible combination of weights and biases, right? Best possible means the value of that weight and bias will give me the most close value to the actual correct value of age. So can you tell me what was the ML term which was used to understand how a model finds out the best weight and bias? What was the term for that?
Optimization.
Optimization, right? So optimization. So optimization was the process which this ML model used, and through that optimization, it found out this A star, which is the best weight, and this B star, which is the next best weight for this particular feature, right? This was the process of optimization. How does an optimizer know which weight is best? Can anyone tell me that? Like suppose I have A1, A2, B1, B2. How will the optimizer tell me that whether this combination is better or this combination is better? What do you think?
Loss function.
Loss function, right? So there we have another term which is called as, one second, I'll take a different color. So yeah, so you have another term called as loss function, right? And loss function simply tells me that whether my current model, which has learned some value of this A and B, is it good, or whether my current model with this value of A and B is bad. That's what a loss function does. So what does a loss function do? Loss function will basically tend to show the quality of the optimizer. And what will the optimizer do? Optimizer will tend to minimize the loss function, right? Simple cycle. Loss function tells you how good your particular optimizer is, and what the optimizer does is it keeps improving itself by minimizing this loss function. Okay, so this is the crux of how machine learning works, and this is the crux of how a particular model is built. So if machine learning with so many models that you might have seen in MLT, MLP, it is having so many good models, this all functions and all this thing is working well. So why do you think we need some other setup like deep learning? What is the motivation for that? If ML is working fine, why is DL needed? DL is also going to do the same thing. DL will also find this model only, nothing else. But why do you think we should go to DL?
So to find even more deeper patterns in the data.
Yeah, exactly. That is a good point. And the second point is that if you see real world data, when you work in a company or somewhere, and those of you might have worked with some real world project, when you work with real world data, do you get data like this, like proper Excel sheets, proper clean data, good numerical features? Is this how you get data? You might in some cases, but is it the only way you get data? Is that right? Okay, let's take an example. You have an example of an email, right? So I'll take a new page for this. Yeah, you have an example of an email, right? So what is an email? Is email a feature like this X1, Y1? Does it look like this, or does it just look like a plain text?
Plain text.
Plain text, right? But when you in this email have this classification of spam and non-spam, that is ML, right? ML will identify an email and it will say that this particular email is spam and this particular email is non-spam. For example, I say an email, you won a lottery. So I use this word lottery. So this email most probably is going to be a spam email, right? So how does how does a model actually find out which inside this unstructured text data, which email is spam or which email is non-spam? That is a very difficult task, right? It's not a very simple thing. In regression, you will do what? AX plus BY is equal to C. These type of patterns are very difficult to find when my data looks like this. On the other hand, if you see there is an image, you get images like this and you have some fruit inside this and you want to find out which fruit it is, right? So for example, you might have used ChatGPT, you upload an image there and you tell that remove the background color of this image. How does ChatGPT know what is background? How does ChatGPT know what is background color? It has to interpret the image for that, right? But does a simple linear regression model or a simple logistic regression model, will it help you to actually find out such difficult patterns in an image? It can't, right? Because all these models are built upon very small functions. They cannot actually decipher such heavy patterns in unstructured data, right? So because of this issue, we cannot actually use machine learning to solve real world problems. We have to move beyond machine learning. And there we come into the world of deep learning, okay? So because of the failure of machine learning to adjust the patterns of real world data, we have to move into deep learning.
So, can we say that deep learning is mostly focused on unstructured data? And
yeah, that is what we use it for.
still
Because for
prefer
structured
ML.
data, we have ML, right? So if you have ML, what is the need for deep learning in that? It is focused on unstructured data. That is the crux of it. Okay, so this is unstructured. Mostly what deep learning works is in 3 dimensions. One is text, okay, for which you now have LLMs. Second is your images, and videos are also part of that only, for which you have convolutional neural networks and advanced versions of that. And the third is your audio, right? And for this audio, you basically have some speech models, which I think is what your project is about this time as well, right? So these three types of unstructured data is what deep learning helps us decipher. Deep learning will actually build the same models like this only, but because deep learning models are so massive in size, even the result it gets for building a simple model also gets magnified. Your regression models and classification models, the traditional ones which you have seen, they are very small model and they actually cannot work on data which is like in millions. In deep learning, you have millions of data, you have billions of text and images. All of that can be handled with deep learning very simply. That is the main point. The first point is the data being unstructured and real world. The second point is that the data is actually very large. It is very voluminous. Okay. And because of that heavy volume of the data, traditional ML models cannot support it. So because of that, we have to build custom deep learning models, which will help us get some results out of that. That is the main idea. Okay, so are we clear now what is the main need for deep learning and why our simple ML does not help us in that? Any questions on this? Okay, so I think that is fine. So we can move on to the first topic of this was just some motivation to start off with. So let us now move on to our first topic. So I'll just erase this a little bit, so make some space. Okay. So basically, for illustrating some of the topics in this week, we'll take classification as the problem. Okay, so classification. So in classification, what you can think of is the image problem, right? Which is what type of fruit is inside an image. That is a classification problem. Or taking text from an email and saying this is a spam email or a non-spam email. These are traditional classification problems, right? Now, if you know for classification problems, we have some famous ML models, which can be your logistic regression, which can be your Perceptron, and so on, right? These are quite famous ML models that have actually been built. Okay, this model, which is the Perceptron model and the logistic regression model, these models have been scaled in real world to convert into deep learning models as well. So the simple Perceptron that you have and the simple logistic regression model that you have, these models have been modified in the deep learning world, and through them we have actually built the first deep learning models, and that is what we are going to start with learning. Okay. So before we move on to this, we learn about the first actual built deep learning model, which is actually a very basic model. You'll see it's actually a very useless model, to be honest, because it does not have very much applicability in the real world. But this was the first attempt to build something in deep learning. Okay. So this model was called as the McCulloch-Pitts neuron. So MP neuron, that is the name of it. So what this McCulloch-Pitts neuron does is very simple. It only works with the input. Okay, let's talk about what it does. So McCulloch-Pitts neuron cannot work with any real world data. That is why I called it a useless model, because no real world data can actually help it. But still it will help you to understand the logic, how deep learning works. Okay, that's what we'll try to decipher. So what McCulloch-Pitts neuron takes is data of this type. I'll write you, there are two features here. And this is the type of data it takes. So can you tell me what type of data this is? Like if you see this 2 data points, what type of data do you think this is?
Binary.
Yeah, binary or Boolean, right? That is what it is. So it's a simple binary data, which will only take binary input, which is zeros and 1. And what does McCulloch-Pitts neuron do? It does classification. Of course, that's what I'm trying to say, because we are only learning classification models today. What this will do is, it will to classify. So to classify, how does it classify? So to classify, what it will do is, it will take the sum of all features. It will take the sum of all features. And if that sum of all features is greater than equal to some threshold, so this is called as a threshold, this we can decide, okay, this is not fixed. If it is greater than some threshold, then it will say that it is class 1. If it is lesser than that threshold, it will say it is class 0. Okay, so for example, class 1 is spam. So if some of those features is greater than this threshold theta, then I'll call it a spam email. And if it's less than that theta, I'll call it a non-spam email. So could you tell me, for example, let's set up theta is equal to 2 right now. Could you tell me what are the labels for these 2 points? What is the y for these 2 points?
So 0 and 0.
0.
Yeah,
1 and 0.
1 and 0. I'll just write this one differently to show this is the class, okay, not the data point. For example, if I search write theta is equal to 3, will I still get the same thing?
No.
Yeah, it will be 0, 0, right? 0, 0. So it is not, none of the points are greater than theta, so it is going to be 0, 0. So can you now understand why this model is not very reliable? It is not, right? Because if I change the value of this theta, I'm getting very different results for the same data point. And the same email cannot be spam and non-spam both, right? It has to be either a spam or a non-spam. So what the problem is actually happening is that this MP neuron which is there, this is completely depending on theta. Depends on theta,
Hard-coded.
right? So basically, can I say that the model has a little bias to the value of theta? It does, right? Because whatever theta the user has decided, based on that, the classification results can be completely skewed in that direction. There is no uniformity in the classification, right? So that is the main issue. Can anyone tell me what is the other issue from this? Before that, I think somebody raised hand, so I'll just look into that and then we can come back. Any question? Somebody raised hand. I could not see actually who raised hand, so you can unmute if you have a question. Okay, so I think it's fine then. So could you tell me what is the other limitation of this model apart from the theta value? Like, is there anything else which looks a little bit of a problem to you in classification, which is happening?
Sir.
Yes.
I think not every problem can be transformed into binary class or
Exactly, right? So
change.
basically, almost everything cannot be transformed into this category, right? All the real world data that we see, most of it, like actually, I think none of it is binary. Very rarely you will see any binary input. Binary output is fine, but binary input is not fine, right? So this problem that the input is binary, this is not real world. And we want to build a model which is real world, right? So we cannot actually go on with a binary thing which will never get any value, right? There is the biggest issue you have missed so far. So could somebody tell me what is the biggest issue in this? One is, of course, it's not binary. It is binary. Second is the theta value is a big bias here. What is the biggest issue that is happening?
There is no learning.
Yeah,
We have to
exactly.
fix.
There is no learning. That is the problem. When we are building ML models, we want the model to learn. It has to learn from some data patterns of the data, and then it has to basically go on and do something, right? So there is no learning happening. No learning. How can I say there is no learning happening? Because there is no weight. Can you see any weights and biases anywhere? Where are the W's? Where are the B's? You can't see it, right? There is no weight which is being assigned. So how can I tell to my model that this particular feature is more important because it has a higher weight, or this particular feature is more important because that has a higher weight? I cannot tell that, right? So because I cannot tell that, I cannot actually make any distinction on which feature is important. And the main thing for any ML or DL model which you have seen in your ML courses is identifying which feature is important. That is through assigning a weight. Which feature is more important will definitely have more weight, right? But here there is no notion of weight. So because there is no notion of weight, I am not learning anything. And because I am not learning anything, the model is not very useful. It is a redundant model. Okay, that is the main issue with MP neuron. The models that it learns is not useful. So is it clear? Any question on this? Very simple. You just have to add the input, see if it's more than the threshold. If it is, then class 1. If it's not, class 0. Very simple rule. There is no learning that's happening.
Sir, and how the theta is decided?
That is again, that is the main problem, right? It's not decided. You can do any theta if you want. Like I can set up theta equal to 5 for me. You can change it and you can make it 10. There is no restriction. That is the main limitation, right? There is no fixed value of theta. Okay, that's why I wrote it in the limitations, right? Because there is no value of theta. And you saw, right? Just I changed the theta value with 1, like from 2 to 3, and the complete result got messed up, right? So that is the issue.
Sir, and the purpose of mentioning such a model in our course would be like
because it's
why
the first,
are we even talking about
it's
it?
the first neural network that was built.
I see.
That's why. Okay, yeah. Right now you will not find any use case for it. That I can tell you. There is no use case. But because it was the first network, this will actually give you an idea of how a neural network works. So that to motivate that, this model has been taught. Okay, you'll understand when you see neural network in a while, you will see how it was built from this type of an idea only. So basically, what I'll tell you is for today we'll learn 4 models. One is Perceptron. One is this MP. Second is Perceptron. Third is your sigmoid, and fourth is your neural network. So each of them builds on the previous one. It solves the issue of the previous one and it builds something better. Okay, that's how we are learning it. Yeah, it will be available on YouTube. Okay, is MP neuron clear to everyone? Could you just give a thumbs up? Then I'll move on to the next model. I'll assume it's clear. Yeah, okay, great. Wonderful. So let's move to the next one. Next one you've already seen in ML, but it will help you to understand how it was built in DL, because DL works on Perceptron only, but it has built a modified version of the Perceptron. But before going on to that, let's again recap the basic perceptron because that will help us to get an idea of how it works. Okay, so instead of telling you what perceptron is and all that, let's ignore that. Let's just try to do it in this way, that we know there was a model which did this task called the MP neuron, right? It solved this problem. Let's now try to see how perceptron solves the same problem. Okay, so we have inputs now, x1 and x2. We again have a classification problem, so we have a label y. Okay, let me just do it with blue color, that will make it better. Yeah, so we have x1 and x2 as our features, and we have a label y, and we have to classify. Same problem. Okay, the first thing that perceptron does is no binary inputs. Binary, not no binary, it can have a binary input also, but no binary constraint. Perceptron does not require the input to be binary. MP required it, perceptron does not require it. So basically you can have input like this, 0.73, 1, 1.9. These are very valid inputs. You can have any real input which you want. Okay, that's the first constraint which perceptron solved. The second constraint that perceptron solved is basically this model now solved the problem of theta. There is no theta. Like the theta which was there earlier, where like theta could have been 5, 10, depending on what I want or what you want, right? Perceptron does not have any theta. So it fixes the theta problem. There is no threshold now. There is a threshold, but it's not like it can vary. There is a fixed threshold which we'll now use. How do we do that? Let's try to understand the rule, the updating formula of perceptron. With that, you'll understand there is no threshold now. The formula is simple. It will basically take a weighted sum of inputs. Okay. And if this weighted sum of inputs is greater than or equal to 0, so there is no theta, no, it's 0. Okay. The number is 0. Then my class is 1. Okay. That means spam email. And if it is less than 0, okay, so if the weighted sum is less than 0, then my class is 0, which is basically a non-spam. Okay. So from this formula, you can see that there are two major problems that the perceptron has solved. One is there is no binary constraint anymore. Second is there is no variable theta. You have a fixed theta value, which is 0. So the formula is fixed for everyone. You will also have the same formula. I will also have the same formula, right? The third problem is, if you can see from here, from the word here, the formula is taking weighted sum of inputs. What does weighted sum of input means? Weighted sum of input simply means that you now have some weights. Okay, so you have some w1 x1 plus w2 x2, okay, is equal to y. Something like this, not y, but this is the formula, that you are having some weights which have been assigned to the features. Can you tell me, like I just said that a few minutes back, what is the advantage of having these weights? I have a fixed threshold now, so why do I need to add weights here? What is the use of weight?
So the learning
Importance of feature.
Exactly, right? So that's what I talked about in a while back as well. This weight will give you the importance. So for example, in an email, like let's say a first feature is the words, right? What words are used, and second feature is the subject. So generally the subject of an email, it can give you an idea whether it's a spam or not, right? Subject says you won a lottery. Congratulations for job offer. So these are or free internship. These are some subjects which are for spam emails. They're very common to spam emails. So I can say that this subject feature is what I need to focus on. I don't even need to read the entire email. I'll focus on the subject, and from the subject I can decide whether this email is spam or not. So if that is the case, then my W2, which is the weight for the subject feature, it will be more. Like for example, this weight is 9.5 and this weight is 7.5. So that basically tells my model that whenever you get an email, focus on the subject. Subject of the email will give you an idea whether this email is spam or whether this email is normal, right? So this weighting is a very good thing. Now here you can just see two inputs, right? So the weighting may not make sense also, but in real world data, there are thousands of inputs, right? So adding these weights are very important because our model cannot work with endless number of inputs. There is a constraint, right? Because your computers will not be able to handle that. Okay.
So how this weight is calculated?
Yeah, that will come to. Just a recap of what like for perceptron, there is a fixed formula of the weight, but for generally neural networks, we use the gradient descent algorithm to calculate weights. The gradient descent which you have learned in your ML courses, right? The same one.
Yes.
Yeah, and that is going to be our focus on week 2 as well. So we'll go into more details of how it is used, but the crux is it is using gradient descent. For perceptron, we have a fixed formula for the weight actually. That is not a very reliable formula though, and that is why to fix that in the next algorithm which we learn, the sigmoid neuron, that is fixed with gradient descent. Okay, that we will learn that in a while. Okay, but for now, just try to understand that this perceptron will try to get the best weight, which will minimize the loss function and everything. Those things remain the same. But the problem with the MP neuron was there was no weight which was used, right? So this perceptron has solved this problem and it has introduced to us these weights. And these weights basically help us to give us feature importances. This is the main idea. So my MP neuron had three major issues. One issue was the weight was not there. That is getting solved by perceptron. Second issue was there was a variable threshold. That is getting solved by perceptron. And third issue was there was a constraint of binary inputs. That is also now getting solved by perceptron. Okay, that is the thing. So is the basic clear? Like how does the perceptron help to solve us the problem of the MP neuron? Is that much clear to everyone? Yeah, you can go ahead, Prashant.
Also, I want to ask that is classification model means is deep learning based on the classification model?
No. It regresses also. Both are possible. I have taken an example of classification because these earlier models were used for classification. Your advanced neural network, which we'll see in the end of today's session, that is used for both. It can do both the things.
Okay.
Okay. Yeah. Generally, see, the idea is the most use cases of deep learning are in the case of classification and generative AI. These are the use cases, but regression also it does. It can do the same thing. Okay. So these are the basic things of perceptron. Now let's basically try one more thing. Can you help now with all this information? Can we write the formula for the perceptron in mathematical notations? Can somebody tell me how to sum up this formula in mathematical notations? You have everything written on the screen. So just tell me how to convert this formula into mathematics, the rule of perceptron.
Yes,
Ax plus by equal to C.
Yeah, so let's go with the W's and X's for now. So basically, because W's is what we'll be using in lectures, that's why let's go with this. So basically, can I write W1? So basically, not 1, 2 as well. In a general case, can I write Wixi and the sum of this Wixi is greater than equal to 0? Then you have class 1. And if Wixi sum is less than 0, we have class 0. Right? So this basically simply means that if the weighted sum of inputs is greater than equal to 0, then I have the class 1. And if it's less than 0, I have class 0. That is the idea. Okay. So this rule, please learn this. Like you must be knowing it only, but keep it in mind because this will help you to solve a lot of real world as well as your questions. Right. That will be helpful. Okay. Now there is one limitation of perceptron. Like one limitation that we just learned right now is that this perceptron is again just a classifier, right? It cannot help you to solve regression problems. That is one limitation. But the bigger limitation of perceptron is something which I'll try to just motivate by a figure. I'll do it on a new page. The limitation of perceptron is that it cannot actually. Okay, let me do it like this. Let me draw something for you here that you will be able to figure out yourself. Suppose there are 4 points I have. 1 point is this. 1 point is this. So the color is important because the color denotes the class. Okay, so these are class zeros, for example. And then I have 2 points, which is class 1. I have built a perceptron and it is working very well on this data. Can you tell me how will it look geometrically? What does the perceptron mean in geometry? From your ML, can you give me an idea? What does the geometric interpretation of perceptron mean in this case?
So it'll basically create a line to separate these.
Line, right? So a plane or a decision boundary, basically. That's what we call it, right? It'll create a boundary which will separate the positives and the negatives, or class 1 and class 0.
So
can you tell me?
What is perceptron? I missed it actually.
Perceptron is just a simple ML model for classification, right? Which you have talked about in MLT, the same ML model, where you basically do the same thing, right? Which is you take a weighted sum of the inputs, and if it's greater than equal to 0, then you have the class 1, and if it's less than 0, then you have class 0.
What is the class 1 and 2, 1 and 0 means?
Like a simple classification classes, right? Like spam, non-spam, apple, banana, like that in real world.
But does it, if you have greater than 0, have no limit, or less than 0, have no limit, does it signify something more or less?
No. The values don't signify. The class simply means that if the values are above a particular point that is 0, then it is a first class classifier, which might be spam in the spam email case. And if it's less than 0, that means it is non-spam. In that.
Why only 0? Why not 1, 2, 3, something and number?
0 was actually, this was researched by the perceptron researchers. So they had come with 0 as the threshold metric. There is no fixed rule because 0 is basically perceptron is a geometric algorithm. It tries to draw a line between the classes. Like these are two classes, right? This is the positive class, this is the negative class, and it tries to draw a line. So the origin is a good reference to see which points are above the origin or below the origin or on the origin. That is why it takes this.
So we can say the perceptron is a way of classification.
It is a classification model.
It's a classification model, like we have others model also.
Yeah, like your logistic regression, your KNN, it's just like that. Okay, just with a different method. Like KNN used to take your neighbors and then take the majority, right? Here,
Right.
instead of doing that, it is just taking a sum of the ratio and just converting that sum to greater than 0 or less than 0. That is the way of doing it.
What special Perceptron do, which is other than the other models? Which because other also classify, right?
Nothing else. In classification, you have many other models. Like each does some, like in some data points, Perceptron is good. In some data points, KNN does well. Somewhere decision tree does well. So nothing special. Just an alternative.
Just alternative.
Yes. The only thing special about Perceptron is through Perceptron, we have moved on to deep learning as well. That we learn right now. Right now, we are just doing the simple Perceptron. Perceptron guided us to the way of approaching deep learning from ML. That is the only significance of Perceptron.
Okay.
That we'll see that.
Just want to tell that I'm not sure these classes are happening, and I really miss in the interaction section and all. Thank you for having the sections and all.
Yeah, sure. We'll have a session on Friday every week at same time. Okay, for all the weeks.
Thank you, sir. Thank you.
Okay. Yeah, so as you were saying about the line, right? The Perceptron draws a geometric boundary between the two classes. So let me just draw it with the black color to not have any class on it. So can you tell me, we have this boundary, which is the dotted boundary, and we have this boundary, which is a straight boundary. Which boundary will Perceptron draw out of these two?
So the straight boundary.
So why not the dotted boundary? Why is that an issue?
So because it's not separating the data.
Yeah, exactly, right? Very good. So because in Perceptron, I want the data point of class 1 to be separated from class 2, right? So here, if you just see the dotted boundary, on both the sides, I have 1 point of this, 1 point of this, 1 of this, 1 of this. This is not correct, right? So this boundary is not good. Whereas on the other side, if you see the straight boundary, this was doing the correct job. Right, on the above, we have the class 1, and on the below, we have the class 0. If you see, there are other boundaries which are possible as well. This boundary also does the same thing, right? So any boundary which is able to perfectly build this classification or divide the 2 points, that is actually going to be good. Now on the other side, if you see, suppose my data is now like this. I'm changing the data now. So let's maybe go down a bit, or maybe we can just change it here itself. So suppose I have this as my one of the data points, and so I'm just changing how the data point looks like. Okay, that's what I'm doing. Everything else is the same. Okay, so this is what I think. No, wait. It's getting a little messy. Let me just do it on this one only. Okay, so there is a blue point here. Okay, there is a blue point, red point here. Okay, and then there is a blue point here as well. Or let's maybe do it like this. Oh, sorry, there will be a red point here, then a blue point here, and then a red point here. Okay. So can you tell me what boundary will now the Perceptron build on this data?
So it won't be able to classify because data is not linearly separable.
Yeah, exactly, right? So if you see any boundary that I build, for example, this one, this one, this one, any boundary that I built is failing, right? It is not able to classify. Why it is not able to classify? Because the data which is there, the orientation of the data is in such a way that any linear boundary that I'm going to build to the Perceptron, it will not be able to classify the Perceptron at all. And why is that? Because the data is not linearly separable. So linearly separable simply means that the data has a particular line which can separate the positive and the negative. So in this correlation of the data, we have no line that can be drawn which can actually separate the positive and the negative, right? So because of this, my Perceptron will fail. So the biggest limitation of Perceptron is it requires linearly separable data.
Why it calling Perceptron? Does it what do you mean by Perceptron or anything?
So that's just a name, just like decision tree or random forest. It's just a name.
Got it. But then why very nice limitation that you do a linear job only.
Yeah, it'll only do a linear job. It's actually so many people call this a linear classifier because it only works on data which have linear boundaries. Otherwise, it cannot work. Okay, that is the idea. So whenever you go to Perceptron, if the data is not linear, Perceptron will not work. If the data is linear, then well and good. Perceptron will guarantee. Okay, that is also there. If the data is linear, then Perceptron will guaranteedly work. So no matter what the data is, if it is linearly separable, Perceptron is guaranteed to have a solution. But if in any case, even if one point of it makes it non-linearly separable, no matter how many iterations you learn you train the perceptron for, it will never be able to get an answer. That is the constraint. Okay, now I have a question for you. Do you think real world data like emails and images, are they linearly separable all the time? Will you have this?
Almost never.
Almost never, right? Because there will be a spam email, a non-spam email, which can also contain a word lottery. Like, for example, I'm organizing a fest in my college and I can say we'll have a lucky draw lottery in the fest. It's not a non-spam, right? But still I have the word lottery inside it, and my perceptron puts it inside spam, and I miss my fest, right? So that is also possible, isn't it? So that is why whenever you work with real world data, the perceptron algorithm also can give you results in some cases. It's not as bad as the MP neuron, but in most cases it fails. So are we clear with why it fails now? Any question on that? Is it clear why perceptron had to be improved upon and why could not we just settle with it?
What is MP neuron? It's a new classification.
Yeah, the one which we discussed. Were you there like 15 minutes back?
No, I just joined a little late.
Okay, so MP neuron is simple. It will only work when the sum of the inputs is greater than some threshold which we decide. Like, for example, if the sum of these two is greater than 5, then I'm doing class 1. If the sum of these two is greater than or equal to 2, then it's class 1. So there is no fixed formula for that. It is very variable. And that is why if every time it varies, then something for me might be different for you, right? By changing the formula. So that's why it's not a good model. Okay?
Okay.
Yeah, you can watch the recording. We have discussed in detail. That will make it clear. Right now, I think I want to go on to the next one. Otherwise, the time constraint is there, right? So you can just watch the recording. We'll not use it anymore in the session as such. So it won't depend on the other topics, okay? But just watch the recording once, you'll get an idea of what it is.
Thank you, sir. Thank you, sir.
Yeah. Okay. So that is the thing. There is one more limitation which I also want to discuss. The other limitation that is there, it's not a limitation as such, but it is something that we have improved upon in modern formulas. The limitation is that perceptron does not tell you how positive or how negative a particular data point is. Like, for example, like suppose I have this value 0.1, right? This 0.1 will be ignored, right? It will straight away convert this into 1, class 1, right? Because it's greater than 0. I have another value which is 0.11. This is also very close to 0. It is actually not very clearly positive, right? But still, because it's greater than 0, I'll straight away assign it class 1. Right? So how positive or how negative that data point is, that is also something which perceptron fails to tell us. Right? It does not tell us like this email is spam, but it has a 60% chance of being non-spam. This type of minute, accurate analysis, this perceptron does not do. Right? It does not tell us how much it is non-spam or how much it is spam. Just it will blindly look at the value. If it's greater than 0, whatever greater it is, it will straight away classify. There is no judging of the data or understanding of the data at all. It just simply applies a math formula and finishes it off. Right? Straight away.
One question, maybe a very silly question. Maybe it helped me to understand the subject.
Yeah, sure.
What is WI and XI means? Maybe explain it a bit.
W is the weight, right? So if you remember, linear regression, you have WX plus B is equal to C. This Y, right? This type of formula you have, right? So X was the feature and W was the weight to that feature, right?
Yes,
Same
yes.
thing. Yeah. So
Same
thing. This, right? W1, X1 and W2, X2. That means X1 is the first feature and W1 is the weight to that. X2 is the second feature, W2 is the weight to that.
So when you say 0.1, 0.11, and so it will talking about weight only.
No. I'm talking about this whole thing. That is this
whole as a compound.
Yeah, this whole thing gives me a 0.11. So if this is 0.11, then my classification will be 1, right? Because it's greater than 0. That is why. Okay.
Right. But doesn't matter, right? 0.0, 0.1 or 0.11.
Yeah, same. All are 1. Yes.
All are 1.
Yeah.
Sir, in MLT, we study that whenever the perceptron makes a mistake, we update the weights.
Yes, we do. Yes.
So can you relate with this? You just mentioned that no real learning is happening. Those minute details are missed by perceptron. I'm not able to relate.
No. Understand that. So what happens, what you learned in MLT is absolutely correct. And what was said there is, for example, I have a point which is positive, like a spam email is there, and my perceptron gives me this WIXI is equal to minus 0.001. So what is the classification? Classification is 0, right? Class 0,
yes.
Which means it's non-spam. So what will happen here is the perceptron will go back, it will adjust this W, let's say it will be W star, and W star XI gives me 0.01. So now it's correct, right? So now it is spam. Class 1 is there, and then the perceptron will stop right away. But on the other hand, if I have a spam email only, not non-spam, I have a spam email, a class 1 email, and my perceptron gives me this formula WIXI is equal to 0.0001. then my classification is what? It is 1, right? Because it's greater than 0. And it is correct because it is not, it is a spam email, so 1 is correct. So I'll straight away classify it to 1 and I'll end it here, right? Nothing else will happen, right? But
Yeah.
if you understand, that is correct. The model is still correct. I'm not saying model is wrong. But don't you think that this had a very good chance of being a non-spam email as well? Because it is so less, the possibility of being spam is so less. Isn't it,
Yes.
right? But will Perceptron fix it here? It cannot fix it, right? Because the classification is correct. It is matching. There will be no changing of the weight here.
Yeah, basically it won't give us any further information just beyond
Nothing.
classification.
Nothing, yeah, right? So what it will just do is it is just blindly applying a mathematical formula. If that formula is giving me a result, if it's correct, straight away go with it. But how correct it is or how accurate it is, that we are not checking. We are just seeing whether the math is matching. That's it, right?
So can you
We are
repeat
not crunching the
part?
data. Could you repeat? The voice was breaking.
Sir, can you repeat this part once?
This part?
Yes, sir. Yes, sir.
Yeah. So this was just a recap of Perceptron. So what happens is whenever in the Perceptron algorithm, the model makes a mistake. For example, this, if you know, this is a negative point. So my model will say it is class 0, right? But actually I know that the class was 1. So in that case, the model will come back and it will readjust the weight and it will again do it until unless I get something positive, the model will continue to work and keep changing the weight. On the other hand, there's another mistake here, which is second situation. I know that the class is 1. The model gave me WIXI, which is greater than 0. So I got the class 1. So it is correct here, right? So because it is correct, the model will not work anymore. But if you see this value is very close to 0, right? Very close to 0. And very close to 0 means it could have had a good chance of having a negative weight as well. And that means it could have had a good chance of being a non-spam email as well, right? But because the label matched with what we have, even with this value, Perceptron will stop here. It will not do any other analysis after this.
So it is a kind of limitation also, right?
It is a limitation because see, the idea is Perceptron will give you the correct class. If the data is separable, it will give you the correct class, agreed, but it will never tell you how correct it is, right? So it's a vague way of saying it. Like suppose that the same example of lottery, right? The word lottery could have been there in my non-spam email also, but because it is just one word, I will classify it to spam. Right? I'm not understanding the data very well. I'm just seeing the math, I'm matching the math, I'm doing the equation, then I'm just finishing it. Right? That is the main issue.
Ideal solution should be greater than at least significantly be in a positive class so that it can handle little bit edge scenario also.
Yes.
Probability wise, right?
Exactly. But yeah, exactly. That is the point. So do you think, like, I'll ask everyone in general as well, what do you think, like, for this situation? I want to know whether the email is spam or non-spam. That I want to know. But I also want to know how spam it is or how much non-spam it is. Okay, a very corrupt spam email will have a lot of spam words, but a very correct email might have one spam word and that also might be a spam, right? So I want to know, actually I want to understand the data. That is the main aim of deep learning, understand the data. So can you tell me, is there any mathematical method or something through which we can actually arrive at this understanding?
We can create some vector of words and which lead to some cluster of spam or no spam and things.
Yeah, that is correct. That is what our algorithm will. That is a very good observation. But what is that term? Like, to understand how much of something is something. The mathematical statistical term that we use. Some metric. Like here we are doing sums and differences and thresholds. Is there any other mathematical metric that we have?
The regression.
Confusion matrix.
No, don't go into that much complicated metric. A very simple one. So I'll give you a hint. It is the heart of your stats 1 course. Yeah, probability, right? So can I say there is a 60% probability that this email is spam? To 10% probability this email is not. That gives me a better analysis, right? A better conclusion to explain, right? So that is the main limitation. My Perceptron will only give me a value. It will never give me a probability, right? So we have to arrive at some model which will give us the probability as well. Now the mechanics of the model is going to be very similar, but just I want the output. Instead of the output just being a 0 or a 1, I want the output to be of some probability, which will give me a better conclusion to my model. That is the idea, right? So to build that probability, we have gone into the next model, third model for today. Let me just erase this again to make
What
sense.
is activation function? I don't understand this word.
Yeah, we will come to that. We have not come to it so far.
Sure.
We'll come to that. Okay. Right now, just ignore it for now. Okay. Activation function is a very simple thing. It's one of the most important concepts of your course, and we'll come to that in just 2 minutes after this. Okay. So for now, just ignore this. This is a diagram. Okay. I wanted to show the diagram here. I'll explain that later. So to solve this problem of a perceptron, we came to the next model, which is called a sigmoid neuron. Now, sigmoid neuron is 99% same as perceptron. There is no difference. Like this WIXI this thing is still there. I take a weighted sum of inputs and I will again do some classification, class 1 and class 0. Right? This classification is also going to happen.
It's
But
9
the way,
o'clock.
yeah, could you repeat?
Nothing. Please carry on.
Okay, yeah. So what I'll do is the aim of this sigmoid neuron is through these weights and through these features, this sigmoid neuron, instead of telling me whether the class is 0 or 1 directly, it will help me get a probability. Okay, it will help me get a probability. That's the only thing it will do. And how does it help us get a probability? It simply helps us get a probability by applying a sigmoid function. So I think you all have seen sigmoid function in MLT also. Does anyone remember what the sigmoid function is? It is used in one ML model as well. So could somebody tell me the name of that? A very simple ML model. Yeah, exactly, right? Logistic regression uses that. So what does sigmoid function do? Sigmoid function will take some input. So let me call it input here. And it will convert it into this formula. This input. Okay, this is the formula that it uses. So this you please remember as well. So 1 upon 1 plus e to the power minus of that input. What is the advantage of this formula is no matter what value of input you put inside this formula, the output of this formula will always be between 0 and 1. Okay, always. Like you put infinity, sorry, not infinity, you put any very large number, you put 0, you put a very negative number, you put a fraction, anything if you put, the value, the output will always be between 0 and 1. And we already know, right? Probability is also something which loves to be between 0 and 1. Right? Probability is always going to be between 0 and 1 as well. So that is why, because the sigmoid function will give us the probability, we use the sigmoid function in the sigmoid neuron.
How is this mathematical thing able to understand by the value and graph value, it landing of 0 1 only, but how am able to relate this thing in mathematical model and little bit function how come into picture?
Yeah. Okay, so that's why I wanted this diagram there. So let me just take this diagram to a new page, okay? Because in this page I think we have less space. So there I'll explain this. Just a minute. Okay, so what happens is, just look at this diagram. This is what sigmoid neuron is doing. Same thing I explained in the math also. Same thing is happening. You have some features here, right? Which is x1 to xn. Some n features are here. Every feature has this weight, which is w1. So for x1, you have a weight which is w1. For x5, you have a weight which is w5, right? So every feature has a weight. What is happening is, firstly, what you are doing is, here, you are doing this. You are doing summation wi xi. That means w1 x1 plus w2 x2 till wn xn, right? You are taking a weighted sum of the inputs, which we were doing in the perceptron as well, right? After taking the weighted sum of these inputs, you are passing it through this function g, and this function g is the sigmoid function. So this is nothing, this is just a sigmoid function. So what is the input to the sigmoid function? The input is your this, right? The weighted sum that we have taken. So what we'll now do is, we will put this weighted sum inside the sigmoid function, which is this, and here you have your w1 x1 till wn xn, right, with the weighted sum which we just took. And after putting this weighted sum in the sigmoid function, we will get an output of between 0 and 1. So this is your output. So are you understanding now? We are taking the data point, which is x1, x2, w1, w2, the weighted sum of the inputs of the data point. We are then passing it to a sigmoid function, this weighted sum of the inputs. And instead of doing like earlier, what we were doing was we were seeing like whether the sum is greater than 0 or less than 0. We are doing some hard classification in that case. So instead of doing that classification, we are putting this whole weighted sum inside the sigmoid function. And by putting this inside the sigmoid function, we are getting an output between 0 and 1. And that helps us to tell us the probability that whether that input which was given, this input, whether it was this percent, 80% spam or 10% spam or 50% spam or so on. So for example, I get an output of 0.9. That means there is a 90% spam email. Right, so I get that idea, which I was missing in the perceptron. Suppose
So
the output is,
how we can make sure that this of represent the entire age equal distribution and doing it, it's not skewed of representation.
That is where your loss function and optimizer will come into play, right? So obviously, the like for example, in the first one of the sigmoid, you get an output of 0.9, but I know from my data that this was a non-spam email, and my probability is saying that it's a 90% spam. So what I'll do now is I will just do the gradient descent, right? The simple gradient descent algorithm I'll take, and I'll back propagate with the gradient descent, and I'll update the weights. Next time I come back here, the weight becomes 0.2, which is non-spam, right? Which is correct.
Sorry, sir. I'm not aware what is gradient descent. Can you help me with the word? I'm little. Just word line is I can pick up quickly.
Gradient descent. So gradient descent, if you remember, I'll write the formula for you. It's you have seen it earlier in ML courses. So it is basically going to do W2. The second weight is equal to the first weight minus eta times the gradient of the first weight. Have you seen this formula in ML, in MLF and MLT?
I skipped the classes actually. I was working, but yeah, I want to study. But
Basically, for example, this is a loss function, right? So your some mean squared error or some loss function.
Okay.
And my W1 using weight 1, I land here in the loss function. That means it's high, right? It's not good. It's a high loss. I want to land here. This is the lowest point, right, of the loss.
Yes.
With gradient descent, what it does is it helps me to go to a W2, which is here, which is at the low loss. Okay. So it helps me reach a good loss function, a good point of the weight where I can minimize my loss. And minimizing loss means you get a good result, right? Loss means a bad thing, right? So if the bad thing is minimized, then you have a good thing, right? That is how it works. Okay.
So it have delta V1 and what is N1 and here?
N is learning rate, right? It's a constant. So in case this formula is not clear, don't worry about it. In week 2, we will again discuss gradient descent. Indeed, that's the main topic of week 2. So we'll talk about it that time. Right now, you can skip the math for now. Okay. Right now, for week 1, just remember gradient descent is the method through which you get to this best weight where the loss is minimized. So this
gradually you get to the something.
Yes, gradually. Yeah. So it goes like this. Like this it goes.
So in order to calculate the loss, are we saying that even for deep learning, we need true labels to train the model?
Yeah, you need true labels as well. Yeah, they're supervised. You're talking about supervised, right? Supervised or unsupervised. This is supervised for now.
Okay.
So there are unsupervised techniques as well.
Okay, got it.
Yeah, there are unsupervised as well. But for now, the classification that we are learning, these are supervised techniques. You will have a label, in the data.
Okay.
And loss functions are also going to be very similar to what you have seen in ML. Like for regression, you have the mean squared error. For classification, you have the entropy, right? Cross entropy. So these loss functions are going to be the same. Okay. We'll again, loss functions and gradient descent and all, we'll study in more detail next week. But right now, just remember the same setup of ML. Whatever setup you saw in the MLT course, the same setup is continuing. Just the model is changing, right? Everything else is same.
Yeah.
Okay, so I hope you got an idea of how the sigmoid, everyone I'm asking, you got an idea of how the sigmoid is working, right? And why we are using sigmoid over the perceptron. That is clear, right, to everyone? Okay, that is great. Okay, so if that is clear, so this is basically the main crux of deep learning. Now, the main problem, there is no such limitation with sigmoid. There are limitations with the sigmoid function as such, but that we can ignore for now. The sigmoid model is pretty good. It does a good job. Okay, but the only issue with a simple sigmoid model is that this model is too simple. As I was telling you that in deep learning, we are trying to solve very complex tasks, right? We are trying to solve tasks like detecting things from an image or ChatGPT. ChatGPT works with a deep learning model. What is coming next? ChatGPT does so many complex things, right? Which your normal model can never do. So how does this type of a small model help us do such a complex task? Actually, it can't. The answer is simply no. This simple model cannot solve any complex task. It will give you good results for simple tasks, but for complex tasks which are very advanced, just a simple setup like this will not work. So the solution, what is the deep learning solution to this?
Can you give us an example where this kind of model will also work? Simplistic model.
Like for example, you have 30 emails or 300 emails, which are very 2-3 line emails. You first convert them into vectors and then you use one sigmoid neuron. It will give you a result. But on the other side, if you have 5,000 or 5 lakh or 5 million emails, then the single neuron will never give you good results. Actually, I'll tell you one thing. There is no hard and fast rule here. It will be all data driven. You have to run the model and see that. That will not give you a good result. That's what these are actually all experimental results only. Okay, these are not any theory. Many of these have been experimented with, and most of these have observed that when you use just a simple single sigmoid or a single perceptron, it will not give you a good result with complex data. With images, it might even fail. Like you get a loss function of minus infinity. That is very bad, right? So in these cases also happened. But on the other side, there's a flip side. The first side is that if you have complex amount of data, this simple model will not work. But is the model bad? Model is still good, right? We argued like from the past 1 hour, we have argued that the model is good. It is doing a good job, right? That's why we have built up from the MP neuron to the perceptron to the sigmoid. It's a good model, but it is not able to solve very complex cases. So it's a trade-off, right? So the solution to this is very simple. What deep learning proposed was you retain the good model. Because the model is so good, you retain it. Don't lose it. But instead of just using a simple single model, what you do is you combine them. Combine many. Okay. So for example, I have a new model now. So this is, suppose, let's call it model X. This is a new model that I have. Okay, I'm just drawing something random here, but you'll get an idea what it is. Initially, this model has a perceptron inside it. Then I link this perceptron to some sigmoid here. Then I link this to another sigmoid here. And then I get my output, final output. So my same input first went through a perceptron. The output of the perceptron became an input of the first sigmoid. The input of the first sigmoid became, output of the first sigmoid became the input of the second sigmoid. So what I'm trying to do is I'm combining my simple models, multiple simple models, and I'm fixing them or chaining them, making a chain of it into a very complex model. Okay, because I know, the argument is I know that this is very good. This is very good. The sigmoid model is very good. That we have argued and we have understood as well. It's a very good model. So instead of just using one sigmoid, why not combine them and form multiple sigmoids or multiple perceptrons, right? That is the
does it not break how it helpful actually at all? If your 0 to 1 value is there, and again you have a 0 to 1 value from sigmoid, right? So it's no adding any value, right? If you're doing
no. Generally, what we do is we do not do 0 to 1 directly. Like we don't use sigmoids in between. We generally use perceptrons and ReLU. There is another model called as ReLU. So we use perceptron and ReLU first, and in the end we use sigmoid. That is how we combine. Okay. Yeah. So I'll come to ReLU, but I'm just saying that the idea is we take multiple good models, we combine them into a chain, and then we get a final model. That is the idea. Okay.
But addition or composition of parallelism of this model, does it helpful or not helpful? It is experimental thing only, right?
Yeah, and with experiment only it has been found. It's very helpful. It is able to do the job. Okay. So now let me just firstly, before going to don't concentrate on this diagram as such, but the idea was that take many models, many good models, small ones, combine them and get one huge big model. That is the idea. Okay. The name of these big models which are there, this model X in deep learning, these are called as neural networks. This is the term you'll hear a lot now. These are called as neural networks.
We call it combination of models in neural network, is it?
Yeah, it is a combination of multiple perceptrons or multiple sigmoids or multiple ReLUs. ReLUs, I'll tell you what that are. So it's a combination of multiple things, right? Another term for neural network is MLP. So not machine learning practice, MLP. So MLP simply means multi-layered perceptron.
Perceptron is so much important. We calling this thing.
So actually, the first neural network which was built was with multiple perceptrons. So that is why it retained the name from there. Now we don't use multiple perceptrons. We use more sigmoids and other things inside it. But initially, the one which got made first, it had a multi-layered perceptron. So actually, that time sigmoid was not much discovered. So they took multiple perceptrons and combined multiple perceptrons together. So that is why this name came, and this name has been retained because it's the first one. So they have honored it and retained this name. So neural networks are called as neural networks. They're also called as ANN because it's artificial, right? Because actually neural network, how does it make this name? It makes a name from the biological term. In our brain, we have neural networks, right? A nervous system, central nervous system, which we have in the brain. So that is a link of a lot of neurons, right? In the body, biological neurons. So from there, they have actually inspired this term of neural network. So ANN simply signifies artificial, right? Because we have created it in computer science. It's not the real one, which is inside us, right? So there are also other names, like there is a hybrid neural network, new names have come up, and multiple such nomenclatures are there. But the common ones that you'll see is ANN, neural network, and MLP. These are common terms which mean the same thing. Okay. So in the lectures also you will see many times the word ANN has been used, many times the word MLP has been used, and so on. So it means the same thing. So don't get worried about it. It's the same notation for the same thing. Okay. Okay. So I hope this is clear so far. So are you able to understand this? Like, might be a little confusing at first go, but I think it's fine, right? The main idea, think of it as combination. So when you think of it as a combination, it will get easy to understand.
It takes so much time to come with this formula mathematically, but we have advanced that time also.
Yeah, very much. So I'll tell you, like ChatGPT 5 is trending right now, right? So I'm not sure how many neurons are there in ChatGPT 5, but in ChatGPT 1, you learn that in the next few weeks, we'll even calculate it. There are around billion parameters were used, billion neurons were used. So that's such a big combination it is, right? So towards week 10, we'll learn that as
What
well.
is neuron here? Perceptron is also model. What do you mean by neuron?
Neuron simply means, so whenever, that's also again a nomenclature only, since we are calling the word neural network, right, from the biology. So neuron is the basic unit of the network. So each perceptron is called a neuron. So this becomes a neuron.
Okay, we just calling another name, right? Just
Yeah. This is one neuron.
Okay.
This might be another neuron. This might be another neuron.
Thank you for clarifying. It's so much confusing, right? These terms.
Yeah, I understand. These are confusing. Actually, these network, the names here are inspired from biology. Okay, that's why the word neuron and neural network has come in.
Yeah. It's too much weird to understand these terms and keep to this definition. And
Yeah, I agree. It's in the first time it will be a little overwhelming, but with the weeks you'll get very used to it. So it will become very normal.
Got it.
Yeah.
Thank you.
Yeah. Okay, so let me show you a diagram, a good one, so that will give you an idea. This is how a network actually looks like. So if you see, this might be some perceptron here, this might be some sigmoid here. Generally, we use sigmoids here. So in the hidden layers, the earlier layers, we don't use sigmoids. Again, that is also a question which will be answered soon, so don't worry about that, but this is the convention. Another one which I told you about was ReLU. We'll come to ReLU in a while. So suppose ReLU is here, another perceptron, here might be a ReLU, perceptron, and so on. Okay, so this is how network looks like. So there is basically some models here, then you have some models here, then again you have some models here, and then it finishes. So this whole thing is just one big model, but inside it has multiple units of perceptrons, multiple units of sigmoids, and so on, which are operating. With this one observation, with these arrows, can you tell me something from looking at these arrows? Is it telling you something about the connections between so many models? Like, can you identify some pattern?
So each neuron is connected to another neuron.
Exactly. So suppose I tell you that find me a path from here to here. You can find me a path for sure, right? There's a path here. There is a path here, right? So every neuron is connected to every other neuron. So can I say that neural networks are, if I say this, fully connected? Is that good? Like, can we agree to this? It's correct, right? Because every neuron is connected to every other neuron. You have a path. Just like if you remember in your CT and Python, you had learned about graph theory, right? Connections in a graph. So it just looks like a graph. Everything is connected to everything else, right? There is a connection there is a path, a simple path from every neuron to every other neuron, right? That is the main idea. So whenever we talk about neural networks, there is always going to be a connection. Okay. Now, some nomenclature again to help you out with this. I'll just tell you some nomenclatures which you can remember for the other weeks. So whenever we have neural networks like this, there can be many layers here. So each of these is called a layer, right? So this is one layer. This is one layer. This is one layer, right? And inside a layer, you have many neurons. This is a neuron. Now, there can be as many neurons you want in one layer. There can be as many layers you want. Like a network with 5 neurons and 5,000 layers. 1 neuron and 10,000 layers. Anything is possible, right? There is no fixed thing inside this. The first layer that you see is called as the input layer because you have the inputs that go into the model here. So your X1 goes here, X2 goes here, X3 goes here. Layers in the middle, whatever layers are in the middle, these are called as hidden layers because there is no input here, right? Exactly. The input has gone inside this and some processing has happened and then you see the output here. Okay. That is what my layer 2 means, hidden layer. I can even have another hidden layer inside this, another inside this. So as many hidden layers I want can be there. And finally, we have the last layer because here we get the output, right? So for example, the output was 0.9. So this output will come out here, right? So that is why this layer is called as the output layer. At every layer, we have neuron. And at every layer, we have as many neurons as we want. And every neuron on every layer is connected to every neuron of every other layer. There's a full connection which is happening, right? So this full connection is also important.
We have full collection and we have 2 classification only. Because output is 2 boxes only, right?
Yeah, for now we have that, and even we can have more for multi-class. That is also possible. We can even have more here. Okay, we can even have 1. Actually, see, for 2 classification, we see 0.9, 0.1. Even if we see 0.9, that is also fine, right? We can still classify. So I'm just seeing that as well, right? So any number of neurons can be there. Like generally, we have 1 in the output. For multi-class, we have multiple. Like suppose there are 10 classes, right? So we'll have 10 neurons in the output, getting probability for each class and so on. Okay, so there's no restriction on that.
Or we have any formula or something that input and output is there, then hidden layer is greater than the one, like 3 is there.
Yeah, we have formula. We'll see the formula. Yes. I'm just saying the notations first, then we'll come to the formula after the notation.
Okay, some relationship we have, right?
Yeah. Everything is related. Okay, mathematically. Yes.
Okay.
I have an example also. I'll show that with the numbers, actual numbers. I'll show that. Okay. So I hope this is the notation. This is clear. One more thing. Where are the weights? Can you see the weights? Like we need weights, right, for the features. Can you see weights anywhere?
No.
These are the weights.
Yeah, we need to put some value, but yeah.
But that's what I was saying. These are the arrows are actually the weights. So what does this mean? This is the weight from this part, this neuron to this neuron. This is the weight. This is the weight from this neuron to this neuron. This is the weight from this neuron to this neuron.
Okay. Summation of all weight will be 1 only, right?
Yes. So these are all the weights. No. Summation of weights are not 1. You can have any values. Summation of probabilities are to be 1 in the output, not in the weights. Weights can be anything.
Weight is proportional to the, suppose S3 is the input, right? So
yes.
S3 having some distribution of 4 hidden layer neurons are going. So the weight will be 0.1, some summation of weight will be also 1, no?
No restriction on that. Summation of weights can be anything, any real number. Okay, no restriction.
Okay, so but suppose something coming in the system is S3, then it going out is more than that. So it's amplify it out kind of.
Yeah. Amplification is happening, but there is no restriction that some has to be 1 or some has to be some t. Some is variable. It can change.
Oh, okay.
Okay, so these were the weights. So I hope the notation is fine, right? We'll now see a numerical example through which you will understand how the processing is happening. Notations are clear, right? For everyone?
Yes, sir.
Okay. Now there is one more thing that comes in. What is an activation function? That is a term that you will see a lot, I think, in the lectures you might have seen. So what happens is every time, okay, let's ignore that for now. Let's try to understand the mathematics first. Through that, we'll understand activation functions. So let's draw a simple network here. Very simple network. So we have 2 neurons here. Or let's even make it even more simpler to make you understand. Because once you understood with the simple one, the same pattern, only the matrix and all becomes larger. Everything else is same. You only have one input, you have 2 hidden layers, and you have 1 output. Okay, so this is my input layer, which you can see here. This is my hidden layer with 2 neurons, and this is my output layer. Okay. So in the input layer, what I have is this input, let's call it x1. Okay, this x1 is my input. Here, obviously, it's fully connected, so I'll have 2 weights here. So I can call it W11, I can call it W12. And here again, I'll have 2 weights, so I can call it W21 and W22, right? Fine, 4 weights I have here, and this is my x. Now, what is going to happen is, firstly, these you can assume this is a simple perceptron here. This can also be a simple perceptron here, and this will be a sigmoid. Okay, this is my structure. I can even change it, but you should know that it is up to you, right? You can change it in any way you want, but right now I have gone with this architecture. I have some perceptrons in the beginning, and in the end I have a sigmoid. Okay, so how does this network give you an output? Very simple. Just keep applying the rules again and again, the same basic rules you have learned earlier, and you will get an output. Firstly, what happens is in perceptron, you know that you have to take a weighted sum of the inputs, right? So how will you take a weighted sum of the inputs? You simply take W11 x1 plus W12 x1. Okay, this is the weighted sum. You have 2 weights. You just have 1 x, so you just multiply the weight with both the weights with the x, and you get the sum, right? Now this sum which is there, this sum is what? This is the output of first layer, right? So I can call it O1, which is the output of my first layer, because I have layer 1 here, I have layer 2 here, and I have layer 3 here. This whole thing is the output of my first layer, so I'm calling it O1. Okay, this O1 which is there, this O1 is the input now to layer 2. That is the meaning of connection, right? The output of the first thing is the input of the second thing. So if you see a pipe like this, water flows from here, then it goes to here, and then it goes to here. Same thing is happening here as well. My input got modified here. It became the output of my first layer. And because it's connected, the output of my first layer is now the input of my second layer. Is that clear to everyone? Are you getting an understanding from this? Is the first layer clear?
Yes, but the layer is hidden and it's distributed in 2 parts.
Yeah. So again, the same thing will happen here as well. So basically what happens is this will, instead of being numbers, this weights and all will become matrices for that. Okay, I'll show you a numerical example also, but right now just I'm trying to explain the chain. Okay, now let's suppose let's just call it some Z1 for now, just some notation because it's a big thing, right? I'm just calling it Z1. Now what will happen is in Z1, when it's reached this part of the hidden layer, same process will get repeated. Because again, it's a perceptron, right? So I have to do the same thing again. So what will be the process now? I'll have Z1 into W21 plus Z1 into W22. Okay, same process got repeated. And now again, I have some output, right?
Little confusion. Z1 is a, I have only W11, X1 is a as a Z only, right? So, but we consider whole layer sum as a input to for the next function.
Yeah. So this was the whole layer sum only, right? Of the first layer. This was a
Yes.
layer sum. It got into some constant or some vector. For now, we'll understand that in a while. And this vector basically became the input to the next layer. So again, I have taken this vector now as my input. So instead of X, now I have this Z, right? This Z got multiplied with these weights here, and I again modified and got some new input.
I have a question. The Z1 value is stored in which neuron, by the way? Like there are two neurons in the hidden layers.
No, neuron does not store the value. Z1 is actually not a, so that's what I wanted to say here. Z1 is not a constant. It becomes a vector. Whenever you have multiple neurons, you get a vector here instead of a constant.
Since I can see two neurons in the hidden layers,
No, it is like this. It is like this. See, this is X1, X1, two copies of X1. Here you have W11, here you have W12. So I see this connection and this connection. This becomes the Z stored in the first one. This becomes the Z stored in the second one, like a vector. So it's going to be like this. Okay. So here will be the first part of Z. Here will be the second part of Z. Like this, it will get stored.
Okay.
Okay, I have an example here that will make it clear to you right now. Okay, right now, I wanted to explain the chain, how the chain is working. Okay, so just understand the chain. The chain is simple. At first step, I have input. I have weights here. I'll again take the weighted sum, the perceptron weighted sum. I'll get some output. Because it's a network, this output of the first layer is now the input of the next layer. And again, at the next layer with this new input, which is Z1, I'll again do the perceptron by multiplying the weights here and here, and I'll again get some output. So this is basically my O2. Okay.
Not
Now,
able to understand this point, how this Z1 is entirely coming as a W21. I will say that W21 will be combined only with W11 only. But we're mentioning as a
Yeah, that's what I'm saying. Z is a vector, right? So forget about the Z. It's just a vector. So it is again getting multiplied like this. It's a vector. Like this, it's getting multiplied.
It's getting okay. It's a vector.
Yeah. Right now, I'm just saying that just understand the chain, how the chain is working. Okay, it's a
this
vector.
diagram itself wrong, right? Because it not represent the entire Z as the input for the W21 also. The W21 may be having some feature of the hidden two boxes of two perceptron coming participate in W21 as a weight.
Right. No, the diagram is not wrong. The point is the Z is not a constant, it's a vector.
It's vector. Okay.
Yeah. The diagram is going to work in the same way, but this Z is not a number. It's a vector like this. So it's a vector multiplication what is happening. It's not a number multiplication. We are multiplying.
W21 is also a vector, or it's just a constant?
W is a constant, right? It's a constant. So this Z is a vector of two parts, which is this Z1, let's say Z11 and Z12. So this one gets multiplied with W21 and this one is getting multiplied with W22. So right now it's happening like this.
Okay. Inside the heading, same thing.
Yeah. It is this is might be a notation confusion. The Z is not a constant, it's a vector. Okay. Now why I'm writing in this notation? Because
Z1 only. Z1, 1, 2, and 2 we not discussed. So I consider them there's a combination. Sum is there.
Okay, no. It's not a combination. It is a vector multiplication that is happening.
Okay.
Actually, why this notation? Because you have to actually get comfortable with this notation. Because in the lectures also, in any neural network textbook, you will see notations like this. They will not describe it in the whole matrix thing. Like here in the example, you see here it will be clearly you can see the matrix thing happening, right? But in the notation of the networks, you'll actually see these notations. So you have to interpret yourself. It's actually a vector or a matrix multiplication, which is happening. See, when you have two neurons, you can have a vector. When you have 30 neurons, you'll have to make a matrix out of it, right? In the end. So
yes.
The matrix notation will come in. So that's why I've kept this example that will make it clear. For now, just understand it's a notation. The idea is to explain that the output of one layer will become the input of the next layer. That is the main thing.
Makes sense.
Okay. Yeah. Okay. Now, since this is the output of my second layer, let me call it Z2. So do you think this will now become the input of the third layer? Will that be correct?
Yes. Sigmoid.
Yeah. Same thing, right? And third layer is now a sigmoid. So what does sigmoid do? Sigmoid does the sigmoid function, right? So can I now take up straight away the Z2 and can I do this thing? Is this right?
Yes.
It is right? Because sigmoid will take the input, whatever input it has, it will put it into a sigmoid function, it will give me an output. and this input it had was a Z2, which is the input of the second layer, and this Z2 my sigmoid has taken, and it will give me an output between 0 and 1 from here, and that is my final output of the network. Okay, so what my point was, the network is working layer wise, and every layer there is some computation which is happening. That computation of one layer becomes the input of the next layer, then the computation of the next layer becomes the input of the layer after that, and so on. And in the end, in the final layer, I do my last computation and I get my output. That is the point. Okay, it's a chain. It's a chain of models where input of first is output of first is input of second, output of second is input of third, and so on. Okay, till you reach the end. When you reach the end, then you get the last output.
Can you help me to understand the sigmoid function? How it come to this sigmoid function? But it's very ununderstandable. But it's understandable. We're getting 0, 1 value. I can understand as a black box, but I want to understand as a what thing we have graph is of x, e to power x is something, and then it eventually taking my value from this domain to this domain, kind of.
See, like sigmoid, what it does is it takes some value here, right? Which value can be something, anything. Like suppose it takes 30 or suppose it takes minus 10. It will do some e to the power minus of minus that value, right? That's what it's going to do. Once it does that, that value turns out to be very large. Okay, it's a very large
Very
value.
large.
So when you even, very large value.
For
Because
negative
it's
value,
large,
it become very large. For positive value, it become negative large, right?
yes, and then when
Minus
exactly.
0, 0, near to 1, right?
Yes, so when it becomes very large, in that case, so what will happen? So 1 plus large, this will become very small, right? Because the denominator is very large and numerator is 1, so this value will become close to 0.
Close to 0,
And
right?
when this becomes very small, in the other case, then this will be about 1, something like 0.1.01.
Yes, only,
This
yeah.
is almost close to 1, right? So
Yeah.
that's how it's happening. Okay.
Okay,
So
okay.
the player here is this E. So the behavior of this E, the Euler constant, that is actually changing the values.
Yes.
Okay.
Hmm.
Yeah. So for very large values, we'll have very small results. For very small values of the C, we'll have very large results, right? That will be close to 0 and 1. And because it's a fraction, it can never exceed 1, right? The value of the fraction in this case cannot be more than 1.
Yeah,
Okay.
it's always less than 1 only.
Always less than 1. Yes. Okay. So I think, that is clear. So is the chain clear to everyone? Once you understand this chain, then multiplying matrices and all is very simple. That is, we'll see that the example will look very simple, but this chain is just get an abstract idea of how the thing is happening. Okay. So if that is clear, so now we can move on to the next part. Next part is related to this only. So once you see this chain, there is actually a big problem inside this chain. See this formula and see this formula. And can you help me identify what that problem is? You will get an output. I'm not saying output will not come. Output will come. But is it restricting to something? These are just perceptron formulas. Was there any limitation that perceptron had in its formula? Was there any problem with it?
Value is
linearity.
Yeah, so it had linear formulas only, right? So only in linear data you can use perceptron. Here also, if you see, this formula is linear, right? This is a line. This is a line. This is a line. These are linear formulas. So is there, suppose I have non-linear data like the ones which we saw earlier, which was not linearly separable. Can this help me get the result from that? Or will it get stuck?
It will get stuck because
It'll get stuck,
again
right?
it will
Because
convert
linear.
to linear models.
Yeah, exactly. Right? So what we need is, so if I can say again, I think the space is less, so I'll take on the new page. So can I say that I need something which gives me non-linearity? Right? I need something, right, which will help me get non-linearity, like some different patterns in the data. Rather than just using the perceptron, I need something different, right? That non-linearity which is there is given to me by the activation function. Okay, so activation function is something you will see in the neural network, which is a new addition to the neural network. What activation function does is nothing but it changes the linear model into some non-linearity. The model might still look like the W1 X1 thing only, but it will do some modification on it. And that modification will help me overcome this problem of linearly separable data. Okay. Now there are many activation functions that are there. Yeah.
Sir, how can I connect this concept to the kernel? Because over there also
kernel is kernel is also quite, see, sigmoid was a kernel, right? So sigmoid is an activation function also. It was very similar, but in kernel what you will see is there are some other kernels like Gaussian kernels and so on. In activation functions we don't use Gaussian distributions. Kernels are mostly Gaussian, so in activation functions we don't use Gaussian distributions because, again, experimental, the Gaussian distributions does not give us very accurate results in ML problems, in DL problems, I'm sorry. Okay, so
but the
it's quite
problem which
similar.
we are dealing right now is, yeah, it's similar to non-linearity also. Over there also, because in a certain dimension, we were not able to separate the data, but in higher dimension, we were able to, like, the data becomes linearly separable. So
Right.
here also we are dealing with the same issue.
We are dealing with the same issue, but we are not going to change dimensions here. Now, why are we not going to change dimensions? Because if you see in DL, the input might have the common input dimensions in DLs are in millions. So if you project a million to even a higher dimension, won't that be a restraint on your computation? It will be, right?
Yes,
You have 1 million
yes.
features and you want to make it 5 million by projecting a kernel on it. That cannot be possible, right? Because 5 million features, how will a simple computer CPU handle that? It's not possible, right? And your DL model ChatGPT had 1 billion parameters. It was that big, right? And now data also becomes that big. So that is why we cannot actually do that. We cannot fiddle with dimensions here. So what activation function will do is it will not fiddle with dimensions, it will fiddle with values. Okay. So instead of changing x1 into x1, x2, x3, it will change the values of x1 and make it such a way that the non-linearity problem of perceptron gets solved. That's the idea. Okay,
Not
so
able to understand what is actually changing. X1, how the input can be changed by.
like for example, there is a simple function called ReLU. Okay, let me show you that, and I think that will make you clear. So what ReLU is doing, suppose my input is negative, like -5, it is changing it into 0. Suppose my input is +5, it is doing nothing on it. So you can see a distribution, right? So if input was negative, it became positive as my output. If input is positive, it remained the same. Okay, same thing is happening.
What is the benefit of ReLU you actually see?
ReLU's benefit is that the linearity problem of perceptron gets solved by ReLU. ReLU can help us understand non-linear patterns as well. But it is not doing any change in the dimensions, right? Your dimensions is still this. Suppose you have data with x1 here, you are not changing any dimension. You are just changing the values. Negative becomes positive and positive always stays positive, right? So you're not increasing the features. When you were using kernels, you were changing this x1 into x1, then x2, x3, and so on. So you're creating more features by changing more dimensions of that, right? In ReLU and other activation functions, you're not changing any dimensions. Dimensions remain the same. You're only fiddling with the values. So x1 will become x1 new, something like that. Dimensions won't change.
Kotti sir, can you just brief me what is kernel means actually?
Kernel is a function which will change one feature into multiple sub features. Like it's not that exactly, but right now you can assume it does that. It changes the dimensions. You're like
adding more
dimension
dimensions,
become 3-dimensional, like that.
Adding more dimensions, right?
Yes, adding more dimensions.
So it's complicated itself. It's making things complication, right?
Yeah, obviously it will make things complicated, but instead of that, in activation function, we are not changing the dimension, we are changing the data itself.
So dimension will be same, but we're changing 5 to 10, something like that.
Something like that, yeah. Sometimes, like every activation function does a different thing, but yeah, only the data is changing, the values are changing. Okay, the dimension of the structure is remaining the same.
What change it can bring? Well, I understand this one, but still not able to relate fully and to the end. The activation function is doing some change of the value so that I can have better prediction of the models.
Yes, exactly. That is the idea. It is adding changes to the data so that you basis your data so that your model can overcome fixed pattern learning. In Perceptron, there is a fixed pattern which was getting learned. Now with the activation function, I'm toggling with that. I'm modifying it. Okay, so that the fixed pattern learning is not happening and I can do the learning in a variable and a better pattern. I can have better adaptability of the data. That is what is happening.
And we in my childhood I studied activation function like decay and something. That is a different thing and this is a different thing.
Decay is not activation function, it is an optimization function. That is a little different from activation. We'll come to that as well. Actually, in deep learning, there are three things. One is the model architecture, which we are learning right now. Second is the activation function, and third is the optimization function. So 3 things are there. So the optimization we'll talk about later, but yeah, that decay is a part of that. It's not a part of activation. Okay, now activation functions is going to be covered in detail next week as well. So for now, just because to just illustrate this example, I've taken the example of ReLU. ReLU is nothing. What it will do is it will just change the negative value to 0 and it will keep the positive value same. Okay. So just a quick refresher. Can you tell me how the graph of ReLU will look like?
Just single line till the 0 and then increasing.
Exactly, right? Because any value here will be 0. Right, negative value, and any value here will be the same thing, like 1 will become 1, 2 will become 2, and so on, right? So you have a straight line here. Okay, so we had actually asked this question last time as well. So there were quite a few errors. I don't know why errors were there in the answers, but it's very simple, right? Because a function which will have zero value for all negatives will have a straight line till the negative origin, and it will have a linearly increasing line in the positive origin. Right?
Have you any sigmoid graph and activation graph too?
Yeah, sigmoid has a graph like this. So it looks like this. So this is 0 and this is 1. So your model will always give you values between 0 and 1.
It's something shifted sine graph or cosine graph something. Is it?
Not exactly that, but yeah, it is like it's like a curve, wavy curve, kind of a wavy curve. Yeah.
So, but it's representing very, as we can see, we have linear input and we're getting linear output, right? But here we're not having a same behavior in a sigmoid.
Yeah, so if you see both these functions, what is linear? Linear means like in terms of linear, this is also kind of a linear thing, but strictly in terms of deep learning, linear means this. Everywhere you have a straight linear line, right? Which we were showing earlier. Here also you see there is no straight linear line. You are actually distorting it here, right? Big distortion is there. Here it is, but the whole thing is not straight, right? And here there's nothing is straight, right? Everything is curvy inside this. There is another function called tan h. So I'm not sure how to draw the graph of that because it's slightly complicated graph. Just see in the net if you possible. Tan h. This is a function. See the graph of this. This is also not linear. This is also an activation function. Right?
Okay, there's something going up and then down. Something opposite of this.
Yes. Then there is one activation function which is very similar to normal distribution, which is like this. It is called GELU. Okay, so GPT uses this GELU.
Activation function is not is not fixed one. Maybe activation function have.
Yeah, I'll tell you one thing. In neural network, everything can be changed. Like when you code in your project and your NPP, you'll understand. You can build a network with 5 neurons and 1,000 layers. You can build a network with 25 neurons and 25 layers. Use GELU, use sigmoid, use perceptron. Whatever combinations you want, every different combination can give you a different result. Right? So it's completely changing. Everything can be changed.
How I can talk in terms of language model, because I understand this thing, but I still not make a sentence with this sigmoid.
Language model is basically a transformer. It is a very advanced form of a neural network itself. There are 5 neural networks. With like in neural network, we saw 5 perceptrons right now. In transformer, you have 5 neural networks only, which are inside it, and each of them have some activation function. Each of them has some the optimization function, some form of architecture of neurons. Everything is changing in that.
Got it, sir.
Yeah, we'll cover to that. Actually, that's also going to be covered in detail of this course. Like in week 7 onwards, we'll start talking about that. Okay. Yeah, so that is the thing. So I hope now the idea of why activation functions are useful is that particular thing is clear, right, to everyone? What is activation function? Again, there are many functions. We'll see some of them in next week, some of them in later as well. Right now, just keep comfortable with the idea what activation function does.
It's a very helpful section, I will say.
Yeah, thanks a lot. Okay, so let's wrap up with the example of the whole thing that I wanted to come to. So now that we have learned all these smaller things, we can see how a network works in real world action, right? This example is nothing, it's from the lecture only. So yeah, so what we have here is a very simple network that is being shown. There is another part to it also, which I will have to draw myself. So I think let's do it like this. Okay, so here we have, let's say y. Okay. So what is happening here is in the input, you have 2 inputs. Earlier I showed you 1 input, right? Now you have 2 inputs, which is x1 and x2. Some values are given as well. Ignore the value, just simple math. We'll just understand the process. Okay. Now what is happening is this is the input layer. And inside the input layer, I have 2 neurons with 1 input here, 1 input here. Okay. Then I have the hidden layer. So this is my hidden layer if you see. And in my hidden layer, we have 3 neurons, h1, h2 and h3. How many weights are there here in this first layer? Can somebody tell me how many total weights are there?
6.
6, right? 6. Because 3 from here, 1, 2, 3, and 3 from here, right? 1, 2, 3. It's fully connected, right? 6 weights. Okay. So now if you remember, what I told you was in the first layer, you take all the input and all the weights and you multiply, and that becomes the input for the second layer. Okay. Same thing is happening here. So what I'll do here is I have this input. I have weights here which are given. Now again, that's what I was telling you. Weights are in form of vectors and matrices. So now I think you can understand these were not numbers. These are vectors and matrices, right? So weights are generally stored as matrices, and how to read the matrix is very important. So these are the weights for h1. These are the weights for h2. These are the weights for h3. So can you help me out to write the weights here? Let's see if you can map it out. Okay, what is this weight?
0.2.
0.2. Okay, that is for h1. What is the second weight for h1? 0.7, right?
0.7.
Yeah. What is the first weight for h2?
minus 0.4.
What about this one?
0.1.
Yeah, this one is 0.9 and this one is minus 0.3. Right?
Are we getting this weight from the input, or the model responsibility to define this weight?
No, first weight is assigned by the user by default. So we use some function and get it, and then the model keeps optimizing with the loss function and it gets the best weight. Right?
Okay.
Slowly. Yeah. That is, we'll again learn it in week 2, but for now, just assume this is the best weight. Okay, for now. Okay, so we have all the weights ready. We have all the input ready. So what we now need to do, there is also a bias. So if you remember, in bias is just a constant that gets added, right? There's always a bias which is there. In some networks, bias is there. In some networks, bias is not there. Nowadays, what is happening is we are moving into a trend where we are ignoring the bias. So it's getting removed. But for now, you can keep it out. So nothing happens in bias. You just add it. Once you take the weighted sum, like you do this W1, X1, in the end, just you add the bias, just as a constant. Nothing
Bias is a one time or two time, because we have two input X1 X2. Bias will be
No, one time. Bias is only one time. Bias is not for the input. Bias gets added here, right? Once for here, once for here, and once for here. In the input, we are not taking. We are ignoring it. We don't add it in the input.
Okay, as a result of a hidden layer. It's
Yeah. Only so bias is always only present in hidden and output layer. In input layer, we'll never have bias. Okay.
Got it, sir.
Yeah, but actually in this course we will not use bias too much. Like in some questions we do sometimes, but mostly we ignore bias because nowadays in modern networks bias is getting ignored. Okay, but still in the example it's there, so we'll talk about it. Okay, now what is happening is the same thing, right? The same process that we have learned here, same process will get repeated. Okay, for the first layer. So you take the W, you take the X and you multiply. Okay, and of course these are vectors and matrices, so you have to multiply. So can you tell me how to multiply this? Like how will the multiplication go by? Matrix multiplication, right? So what is this? This is a 2 cross 1, right? 2 cross 1. And this is a, how much? This is 3 cross 2. So can you multiply this? Is it possible to multiply this?
We can multiply W by X.
Yeah, so we can basically just, see, the idea is sometimes what happens is sometimes dimensions are such that you can't even multiply. Like these two matrices cannot be multiplied straight away, right? So what you do is you just flip them up, right? You can just flip the order. That is fine. Flipping the order does not change anything, right? So now here what you have is you have 3 by 2 and 2 cross 1. Now you can multiply, right? Because these two are same. So you can multiply now. So now what you do is you calculate this Wx. You can calculate XW also, you can calculate Wx, whatever works, but in most cases we do Wx because Wx is the way through which the calculations work, right? So you multiply Wx. How will you multiply? This gets multiplied with this. I think this everyone knows, right? Matrix multiplication from maths 2. Anyone who wants me to explain the multiplication? Yeah, that is clear, right? Simple matrix multiplication. Row and columns get multiplied.
One question, right? We have the that in the matrix multiplication, we can one hidden layer less also. Suppose two input is here, hidden can be one, or it always be bigger than one.
No, it can be less also. Yeah, it can be less on the design. So again, just the only thing that has to be ensured is you make it in such a way that it can be multiplied. That's the only thing.
When to have more, when to have less.
Again, on the architecture, completely on your choice. If less is giving you better, you go with less. If more is giving you better,
decide to have more hidden layer.
Generally, it's more because from the experimentation, more was always better to understand better, right? Generally, it's more. But again, no hard and fast rule. You might get a better thing with less also. That is also possible. Like for example, you can actually have, this is input, 3 layers, hidden is 1, then you have 2 output. This is also possible. It's a valid network. This one as well. Okay.
Got it, sir.
Okay, so I think now what we'll do is we multiply. So what did we multiply? We multiplied a 3 cross 2 matrix, which was here, with a 2 cross 1 matrix, which was here. So what is the output going to be? What is the dimension of the output?
3 by 1.
3 by 1, right? So we have a 3 by 1. And if you see the bias is also 3 by 1 because 3 biases, right? So now to this 3 by 1, I will add another bias matrix. This is my Wx. I add a B here. So this is also going to be 3 by 1. So the output is also going to be 3 by 1. Right? So what is this 3 by 1 output? This 3 by 1 output is my Z1, right? Which is the input to the next layer. So now this 3 by 1 output which I have, this will become my input for the next layer. Okay. So basically what we have done so far is we had the input, we had the weights. So we have multiplied and got the weighted sum of the input. We have also added some bias in it and we have got the output. And now we understand that this output will be the input to the next layer. So is it clear so far? Is the idea clear? Whatever we discussed here with the notations, the same thing is happening with the math. Right? Yeah. Others, can you give me a thumbs up if you're clear with, because I can't see any thumbs up so far. Okay. Yeah, good. Okay, so now what we can do is we can actually take this Z1 and we can go to the next layer and do the calculations with the next layer. But before that, as I told you, that we have activation functions, right? Activation functions are used to make sure that we do some non-linearity. So what we can do is on this output, we can apply an activation function, which is what they are doing, the ReLU function. So again, this depends. You can apply sigmoid function. You can do, there is a very popular one called as softmax that can be used. You can use ReLU function. You can use GeLU function, anything. Okay. So now since we have learned ReLU, we'll use ReLU function.
So changing the value in activation function, how it changing the non-real and non-linearity, changing the value from x from 5 to 10, right? How it can be non-linear.
No, it is not changing the data's linearity. It is just changing the way the model is interpreting the linearity. So because you give it a different interpretation, that actually makes the model less biased to the linearity. That's what we are doing. We are not completely removing the linearity. Data is still linear, but the fixed interpretation of linearity which was there with activation function, we are just trying to remove that. We are making it more variable to different value ranges and so on. Okay. And another explanation can be with ReLU. You see that this data becomes this data, right? So you are changing the linearity in some way, right? So data which was like this now has become like this. It has become skewed up like this, right? So the general linearity which was there, that has been removed. Okay. Okay.
Earlier, these terms are looking.
If I mean to say, activation function can be used on hidden layer also.
Yeah, we are using it in the hidden layer only, right? This is after the hidden layer.
That is for the purpose of non-linearity issue.
Yeah, we can use it on hidden layer also. We can use it in the final layer also. We use it in every layer. Activation functions are used in every layer, and in many layers we use different combinations of the activation.
Okay, sir. Thank you.
Okay. Yeah. So coming back to the numbers here, so we did this multiplication, and this is what we ended up with, this Z1. And we understood that we have to also apply some activation function. So what we did was we applied the ReLU function on the Z1. So can you tell me what is the output of the ReLU function? I know you can see it, but just to understand. ReLU will do what? It will just see if the value is more than 0, then it will be same. If it's less than 0, it will be 0. So this remains same. This remains same. This becomes 0. Right? So this is what we have. So this 0.9, 0.1 and 0. So this 0.9, 0.1 and 0. This is my final Z1. And can I say that this Z1 is now the input to the next layer? Can we say that?
Yes.
Yes.
It's also multiplication.
Yes. So we have process till here and we have got Z1. And now this Z1 is my input to my final layer, right? So as you can see, it's not given in the numbers, but I'll just write the numbers myself now. So if you can see in this final layer, again, I have 3 weights, right? From H1 to Y, H2 to Y, and H3 to Y. So let's create a simple vector of the weights. So let's say you have the weight vector is 1, 0, 1. I'm just for the calculation simplicity, I'm creating this. Okay. So again, what you have to do now, you have to again do the same thing, right? Wx. Multiply, you add some bias. So let's again take bias. Bias is 0, 0, 0. So we'll just ignore bias for now. Okay. So let's do the same thing now with Wx plus B here. So what will be Wx plus B? Can somebody give me the value?
0.900.
3 cross 1. And this is, again, of course, we will make this 3 cross 1 as well. So we have to basically see in the output, if you can see, there is only one neuron, right, in the output. So we have to multiply it in such a way that we get a 1 cross 1 output. So how do you think we can get a 1 cross 1 output from this?
We can change the direction.
Can we simply take the dot product? Is that fine? Will dot product give me a 1 cross 1 output?
Rest will be 0. Yeah.
Correct, sir. Yes.
Right. And dot product is going to do what? It will convert the vector into a scalar, right? So what I'll do, I'll multiply these two, I'll multiply these two, I'll multiply these two, and I'll just add them up. So this becomes 0.9 into 1 plus 0.1 into 0 plus 0 into 1. So what this is? 0.9. Okay. So this 0.9 is my output of this W Z1 plus P. This became 0.9. Is this the final output of the network or is something missing? I have come to here. So I have reached this point. I have reached Y. I have added up all these W's. I have used up this Z1. But does there something else need to be done here?
So activation function for the last layer.
Last activation function, right? And what do we use in the last one? We use sigmoid, right? To make a classification. Here, coincidentally, you can even see this value is between 0 and 1 coincidentally. But generally, this is not the output, right? It's not sigmoided. So it can be even larger than this, right? So what we'll do now is we'll do the final activation, which is also called as the output activation. And we'll apply a sigmoid on this. Okay, so we'll do sigmoid of 0.9. So can someone just Google what is the value of sigmoid of 0.9, and we'll just write that and wrap up this problem. Just Google one, what is sigmoid 0.9, and that will be the answer for this. So basically what we are doing is we are just doing this formula, sigmoid formula, right? On 0.9.
0.71.
Yeah, 0.71, right? So 0.71. This
09.
is my last answer and this is my output. So suppose we are working with spam and non-spam, I can say that we have a 71% chance of being a spam.
Okay.
Okay, I can also say that 29% chance of non-spam, right? Probability can be interpreted in both ways, right? From the
Is there any thresholds of saying that to classify it properly? I can say I have still chances, but I still want a 0-1 input.
Generally, we do it with 0.5. Anything greater than 0.5 is 1, and anything greater than lesser than 0.5 is 0. So if you want a hard label, so the hard label for this will be 1.
Okay. And how I can understand that? Suppose I'm not able to understand 0 is spam or 0 it's non-spam. How and this decision is understandable?
No, because this decision is telling you have a 70% chance of being a spam. So then it's fine, right? If something is a 70% chance of being a spam, I can classify it as a spam, right? That is better.
Okay.
Earlier, I was just getting a hard label from the model itself, that 1, 0. So here I'm not, the model is not telling me 1, 0. Model is saying that this input has a 70%
What is
chance
the
of being
value
a
of
spam.
x?
You
What
can
is the
decide.
value of x? What is the value of x we getting? We getting some value of x, right? In this model when input started. So that
Yeah, x value was this, I think. It was given, right, in the figure, I think. Yeah, this one. 2 inputs for that, 0.5 and 1. These are the two values.
So with these two value, able to get, so this is spam or not spam.
Yeah. So suppose these were two values of, like, some way you converted the words into vector and you got this vector. So from this vector of the email, you got the output that this particular email vector has a 70% chance of being a spam vector.
Being a spam, right? Okay.
Okay.
Mm-hmm. Can be reverse of a negation transforms of some output will be also be usefulness here.
Reverse in the sense I did not get the point.
Maybe I turn the definition. I just say the 0 point. I say that spam is a 71%. I would say
Okay.
not spam is a 71%. So how we can understand changing this behavior will input? What changes will do in input to get this a reverse of input?
So you want the what is the chance of being non-spam as the output, right?
Yeah, but in good percentage, like in 71% only. I want a other. Maybe I get in 29 as the answer, but that will give me as an output all itself.
So the one way is you change, like for every input you will get a different output, right? So for example, when you put a spam email, when the network has learned well, then you get a high chance for the spam. When you put a non-spam email, then you'll have a high chance for non-spam, which is low chance for spam, right? So it depends on the input. Every different input will give you a different value based on the data. And when my model has learned well, when my loss function has been minimized, these values will be accurate. That's what we want to do, right? We want to minimize the loss to make sure that the values are accurate.
Okay, sir. Thank you.
Okay, so that was the main thing. Now see, in your exams as well, you'll have to do these calculations like the full flow of a network. This is called the full flow of a network. So you have to work with different networks. But as I told you, don't get scared by these matrices. If you remember this general idea, then these will be very simple to comprehend. Right? We can change the different vector values. We can change different number of neurons. We can change activation functions. But your idea is very simple. At every layer, you do wx plus b. You apply activation function. After that, that output becomes the input for the next layer. Again, there you do this wx plus b and you apply the activation. Same process, just that input of first layer is output. Sorry, output of first layer is input of the next layer. That is the idea. So once you have understood that, you can solve any question by practicing or just applying the same logic.
These all covered in week 1, right?
Yeah, these are covered in week 1, theory part. Practical part is PyTorch, that will be covered in tomorrow's live session. But for the theory part, this is what has been covered in week 1. Okay, that is it from my side. Now, if you have any questions, we can take up the questions.
Sir, how will you decide which activation function we use?
That is actually everything in deep learning is experimental. So the researchers are experimented, and right now the convention, again, this is not fixed. You can change it. The convention is for hidden layers. You use ReLU, GeLU. These are called ReLU family because they are all variations of ReLUs. So the names are also similar, right? ReLU, GeLU, CeLU is another name. So those are used in hidden layers. For output, we use sigmoid, and one more is a softmax that these we use in the output. Okay.
Okay.
Yeah, but you can change. No restrictions.
Sir, we have Saturday or Friday lectures only, right?
Yeah. Friday 8 to 9 will be the theory live session, and Saturday 8 to 9, basically 8 to 10, you can say, will be the practical live session on the coding.
Thank you, sir. Thank you, sir, for lecture.
Yeah, thanks a lot. Any other questions? Is everyone like clear with the week 1? This is the basic. So once you're clear with this, the later weeks will be simple. Okay, practice calculations as well in the after the session. That will help you to get an idea of how it's working. 2-3 questions you have to practice, and it will be very clear after that.